Our final speaker is Yaghoub Rahimi from Georgia Tech, who speaks on endpoint LP improving estimates for prime averages. So please.
Hello, everyone, and thank you very much for having me. So hopefully the last talk will be nice and you enjoy it. So I'll try to do well as much as possible. So my talk is about LP improving estimates for the endpoint. So this is going to be the overview. So I'm going to talk about the background and the previous works in this field, and then I will present you in the main terms and the main sketch of the proof. So what we are going to talk about is based on averages of this form, and this is the average of our interest today, where you have the averages of a function with a weight of one mangold function. So this is somehow the convolution of f and another weight function. So we start with the beginning of this, the methods that they use to work with these averages. So I'm going to start with the Goldbach conjecture. So Goldbach conjecture states that every even integer can be represented as the sum of two prime numbers. And Vinogradov used a similar sum of exponentials to prove that almost all even integers can be written as sum of two primes, with the exception of at most this much number. And the proof is based on the major minor arc for a similar average with the logarithmic weight function, which the average runs over the prime numbers. Later on, we have Bourgain's work, which is on ergodic theorems for the convergence of these types of averages. So they consider an average of this form where this T is a measure-preserving transformation for the function f. And they prove that these averages converge pointwise, and they have the diagonal LP inequality for the supremum of these averages, which is called the maximal function. And later on, they prove that the transformation can be applied to any polynomial for this function. So it's not just, shifting, or it can be any, shift by any kind of polynomial. So the Bourgain's method is based on the high-low technique that is very well known. And these techniques are an efficient way to approximate, to interpolate different inequalities. For example, if you have this inequality for p equal to 2 and p equal to infinity, you can somehow get a similar inequality for p between 2 and infinity. So now let me try to talk about how it comes to the prime numbers and the averages over the primes, not over all the integers. The study of inequalities over discrete sums was first studied in harmonic analysis, and it was started by the work of Bourgain. Later on, Wirdel studied these types of averages over only the prime numbers, and he proved the diagonal inequality for p greater than 1. And this is the title of the paper that these results are, and he used a simpler form of the circle method. Later on, Mirek and Trojan also proved similar theorems, and they revised the theorem of the results of Wirdel in 2013. And so the averages along primes are very special, and Hahn, Crusoe, Lacey, and Fan studied the LP improving of these types of averages, which the LP improving is different than the diagonal inequalities, where instead of having both LP in both sides of the inequality, you have LP prime in the left-hand side, which is the dual norm for the average of this function. And this is only for p between 1 and 2. So the endpoint means we want to study the average for p equal to 1. And Trojan has done a work on the endpoint estimate for the prime averages of the maximal function. And the work is in 2019, and this is the title of the paper. So these are all the things that, a few of the things on the prime averages. There are a lot of different results regarding the averages of a function over different sets. But generally, if we want to look at the whole process of how we come up with these things, Birkhoff studied the first ergodic theorem where they have an average of this form where you don't have the g function here, the simplest possible average, and they proved that this average is pointwise convergent. And later on, Bourgain proved a similar theorem. What Bourgain proved is that you could, removing the g function, you can have, instead of n, p of n, which I mentioned it in the previous slide. Later on, Bourgain, Lacey, and Demeter extend the result to a sum over a function f and a g function, where instead of pn here, you have n. And finally, Crousset and Mirek and Tao, they have a very recent paper in 2020, which they have this general theorem, which somehow combines all the previous ones. So this average here is kind of the maybe the most general that we have yet. So we have the average of a function, and the transformation here is measure preserving. So the average is over f of the transformation of x, and then transformation of x for a general polynomial p. So these types of averages are very general. If we want to look at our own average, if you consider g to be the one-mangled function and p to be a zero polynomial, which means there is no transformation on x, then that's gonna give us the average that we had. And in this paper, what they have is P1 and P2 are strictly greater than 1. And what we are going to study is the endpoint estimate, which P is equal to 1. And when P is equal to 1, most of these estimates are not going to work. And in here, I'll let you know what we did to make it work. And the idea was using the smooth numbers. So this is our average, an equal to average of a function, and with the weight of one-mangled function, which one-mangled is actually at n is going to be 0 if n is not a prime power, and if it's a prime power, it's going to be a logarithm of p. You can actually replace this by log, but having a one-mangled function helps us to have the sum over all integers instead of only the prime ones. But even if you replace it with log, it's going to be the same. So the main theorem here is that if you consider indicator functions f and g over two sets of integers, the average of f inner product with g is bounded by the normalized norm 1 of f and g. So this is the case of p equal to 1. With an extra factor of psi, which is of logarithmic factor, and here we somehow separated when we have the generalized Riemann hypothesis and when we don't. So if we have the generalized Riemann hypothesis, we have a better approximation for the prime number theorem, and otherwise we don't. So and we expect to have a worse bound here for this psi function. Actually, in most previous works, when they want to prove an LP improving function or diagonal LP function, they prove these types of inequality, and then they do a dense argument to extend to from these indicators to a general function. Other than this, we have the maximal function I forgot to mention that here n is a fixed number. So the maximal function is when you take the supremum over all possible n. And we expect a similar inequality. So for the maximal function, we have a similar equality, which this runs over all the sparse collection of intervals, which the sparse collection are somehow, they have a nice definition, which I'm not gonna confuse you more. So, and using this theorem, they have this nice chlorally, which we can, bound the maximal function with the different measures of sets, which it's gonna be a little bit complicated. So my main focus today is going to be on the first term. So let's try to review some trivial facts here. So we have the prime number terms for arithmetic progressions. These sums are running over all integer numbers modulo q. And what we expect is that if you have the generalized Riemann hypothesis, this sum is going to be x divided by its totient function plus an error term. And if we don't have the generalized Riemann hypothesis, they use Page's theorem to prove this. And what we get is an approximation of similar form with a worse error bound. So here you have x to the 1/2, but here it's larger. So, but still this is a good estimate. And in the case when we don't have generalized Riemann hypothesis, when we work with the L functions, they can have roots in the critical strip, and therefore we have some exceptional characters, and these terms appear. So in the case of Riemann hypothesis, this is not here. And the L function corresponding to a real character can have a 0 in the critical stripe. We call that 0 beta of q. The thing is that these zeros are rare. And we call it q, which its corresponding L function has a 0, qn. So they are rare and they can be, far from each other. So if qn is the nth exceptional q, there is a c greater than 1 where the next one is larger than qn to the c. And that gives us the fact that these are far from each other and they are very rare. So in the approximation of these types of sum, the Gauss function appears a lot. And in the classical techniques that they use to prove LP improving inequalities, so they usually estimate the kernel using a Gauss sum. And the Gauss sum is defined over all the characters module q this way. And this phi is the totient function, which is, and this aq is the set of all numbers co-prime to q. So we have these two estimates. One estimate for the Gauss sum, which the Gauss sum is bounded by 1 over square root of q. And another estimate is for a lower bound for the totient function, which is the totient function is much larger than this quantity here. So these are used mainly in the details of the theorems, which we don't talk about, but it was worth mentioning. So the sketch of the proofs for usually for these types of LP improving inequalities is that they approximate the kernel an with another sum which is much more comfortable. For example, here we have one Mangold function, and in order to get rid of that, we need to approximate with another function that is is concerning exponentials and probably some smoothness using Schwartz functions. So we approximate an with bn, and later we try to use a low-high technique that Bourgain used, and later on Trojan used for its endpoint result. So we try to break Bn into low, high, and exceptional part, which this exceptional part comes from the exceptional Qs. And here Q is a parameter that controls these sums. And we need to somehow consider an upper bound for these sums to have a good estimate for each. And later, after having a low, high part, we need to estimate each and then optimize this bounds using this number Q. So let's start with the kernel that we have. So our kernel is sums of one-mangled function, and its Fourier transform is going to be sums of one-mangled multiplied by exponential sums. So this sum is actually going to be very similar. The AN sum is going to be very similar to this next sum, MN, which is sums of delta functions over all integers. And using this prime number theorem, we can somehow relate AN and MN. So considering L to be a Gauss sum multiplied by the Fourier of N, so this is the point where we are going to use this to approximate AN. So this is a very common technique in this literature. If you look in the previous papers, they have a similar form of functions here, Gauss sums and sums of exponentials. So the Fourier of this is going to be sums of exponentials. And using this, we need to somehow approximate A, and then we need to use the minor major arc to estimate each part. So first, we have some trivial bounds for the MN that I just mentioned, which we don't want to go into details. And so to approximate the kernel AN, first we approximate it for the, so if we want to approximate AN at key C, if key C is near a rational point, we can have this approximation. So here, this approximation mainly comes from the circle method, and using that approximation, we can extend into the whole circle by defining some, V and W, V for the whole integers. For any key C in the unit circle, you can define V, and you can smooth out the M function by a Schwarz function, where Schwarz function is a continuous function that looks like a bump. And using this smoothness, we can extend this approximation into the whole interval for our Fourier of AN. And finally, you can write down that AN is approximately Bn, where Bn is sums of those Bn that I just mentioned. So there is a S here which specifies Q between 2 to the S and 2 to the S plus 1. So this provides you with the property of dyadic intervals and the fact that this Schwarz function on each dyadic interval is going to have only a finite number of non-zero A and Q for every key C. So, and using these things, one can show this lemma here. Therefore, we have the estimate for AN using a better form Bn and an error function. And after this, we go to approximate Bn with approximate Bn using a low part, high part, and exceptional part. So it's a very common fact to consider these averages, these summations here. So we had a function Mn and a Gauss sum, and we use a Schwarz function to smooth these numbers. The traditional technique to consider a Vn sum for the low part and a Vn sum for the high part is that to separate these summations for Q less than a number and Q greater than a number. And most of them use this technique. But if we want to use that, then we cannot get the endpoint estimate. So maybe our main contribution comes here when we consider the smooth numbers. So instead of considering Q less than a fixed number, we consider Q to be a smooth number. And so the low part is this summation over a smooth number, and the high part is this summation over the numbers that are not smooth. And if a number is not smooth, therefore it's going to be larger than a fixed number. So the high term is going to be similar to what traditionally they used to bound, but the low part is going to be totally different. So we defined our low term using this V. So we sum over all possible V's that we can have, which S is identifying some dyadic interval. And the high term is going to be, again, a similar sum. So if Q is going to be smooth, therefore this is going to be trivially true. So it's technically, we are putting an upper bound on this, which I mentioned in the kernel approximation, we had some upper bound for Q, and this is where we need that upper bound. Finally, we have the exceptional term, which, since the exceptional characters are rare, we don't have any specific restriction. So this sum for Wn is actually sum over all possible A and Q. Therefore, the exceptional term doesn't have any specific restrictions. So using this, I should mention that we put some part of this W into the high term. So those parts which are greater than Q can come into the high term, because we usually use a brute force technique to bound the high term using the Winograd inequality. And using Winograd AN is small, and then with some computation, high term is small. So we don't actually look at the difference of AN and the high term. We just bound each, and since they are small, therefore we have a good estimate. So here is the part that I mentioned. So we have that the Bn that we had is very small to the sum of low term, high term, and the exceptional term. We had some error for the kernel approximation, and then we get some error for approximating Bn with low, high, and exceptional. And computing this is going to give you a very nice sum, and that sum can be estimated easily, and then we get this one. And next step is to approximate each of these, which is going to be straightforward. The only part that is different than other works is the low part, which we use the property of smooth numbers. So the high part can be estimated with some computation, and the main part comes into the low term. So for the low term, we can actually compute the low part as a convolution of the M function that I mentioned and the inverse Fourier of the Schwartz function with the product of some S, which S is defined as some of these, which C is the Ramajan sum. And this computation of S comes actually from the Cohen identity, and S can be estimated above by a logarithm of Q. And so the major contribution is in the low term. And finally, for the exceptional, we use the fact that the Fourier of Gauss sum is known, and it's 0 if X and Q are not coprime, and it is a small number if they are coprime. And also the fact that the exceptional characters are rare, we get an estimate for the exceptional part, and combining all of these things, we can get an inequality for the inner product of the average with the G function. So the exceptional, this comes from the low term, and the exceptional term is absorbed in the low term because its error is much less than the low part. This part comes from the high term, and we have a right-hand side with respect to Q, and we had some restrictions on Q to make these estimates as small as possible. And therefore, minimizing the right-hand side over Q, we can get an estimate for Q. And what we get is actually going to satisfy all the restrictions that we put on Q. And inserting the estimate of Q in the right-hand side, we can get the inequality that we were looking for. And finally, we get the inequality that we want. And that's the end of this technique. So I'm going to maybe stop here. And thank you very much for your attention.
Well, thank you very much, Yaghoub. I don't know if there are questions. I know Carlos has had his hand up, and maybe that was from the last talk and I didn't see it. Carlos, do you have, I don't know. Let me see if there are. Okay. So thank you very, very much, Yaghoub. That's the for a very nice talk.
Thank you very
and
much.
I thank everyone who stayed through to the end. We're now free at last. So maybe we'll do this again next year. We'll see.
Sure.
Thank you, Mel. This was a great conference.